Okay, so I want you to picture a scenario. You're sitting in a boardroom, maybe a therapist's office, or honestly, you're just scrolling through social media on a Tuesday afternoon,
Right.
and you hear that word, the E word, empathy.
Oh, it is everywhere. It's the corporate buzzword of the decade, I think.
It really is. And usually when we hear empathy, we get this very specific, almost soft focus image in our heads. It's warm,
Fussy.
it's fuzzy, it's holding someone's hand while they cry. It's, this singular glowing light of human connection. It's a virtue.
Exactly. It's seen as a moral good.
Yeah.
If you have it, you're a good person. If you don't, well, you're a sociopath. It's very binary.
It's completely binary, and I have a feeling you are about to completely ruin this poetic image for me, the stack of research you've brought in today, and it is a massive stack. It suggests that empathy isn't one thing at all.
No.
And it is definitely not just warm and fuzzy.
You're absolutely right to say that. If we really look at the neuroscience, and we are going deep today, I mean, from the lesion studies of the early 2000s, all the way up to the connectivity maps of, well, basically today, 2026 empathy isn't a single center in the brain.
So not one little spot that lights up.
Not at all. It's actually two distinct, very high-powered, and often competing systems.
Competing. That's a strong word. You're saying they're at odds with each other.
It's the reality of the architecture. I mean,
Yeah.
they're wired differently. They live in different neighborhoods of the brain. They evolved at different times. And frankly, they don't always get along.
So are we talking about some kind of civil war inside the skull?
In a way, yes. You could think of it like that.
Yeah.
On one side, you have what we call affective empathy. This is the hot loop.
The hot loop.
It's visceral. It's millions of years old. If you see someone slam their finger in a car door and you physically wince, your stomach drops, you clutch your own hand.
Oh, I do that.
Yeah, that's affective empathy. It is automatic. It's emotional contagion.
Okay, so that's the I feel your pain hardware.
Sure.
A raw feeling.
Precisely. And then on the other side, sitting up in the penthouse of the brain, you have cognitive empathy,
The cold loop.
the cold loop.
Yeah.
This is the knowing system. It's deliberate, it's intellectual, and it is slow. It's looking at that person with the smashed finger and calculating subject A is in pain, subject A will likely require ice and a ride to the ER.
So you understand the perspective perfectly.
Perfectly. But your heart rate hasn't changed a beat.
That is such a stark difference. I feel you versus I analyze you.
And the mission for this deep dive is to physically map these two experiences.
Yeah.
We aren't just talking about psychology concepts today. We are talking about, cortical thickness, gray matter density, and network connectivity. We're going to see how the science has moved from just finding the on switches
That one.
to understanding how these systems actually talk to each other.
And I see in the notes here, we're going to talk about what happens when they don't talk to each other very well.
That is where it gets really, really interesting. We're going to look at what happens when the wiring compensates. What happens in the brain of someone who can't feel but can understand, or, the other way around.
I love it. We're going from the what to the where, and most importantly, the how. So let's unpack this. Where do we even start?
We have to start with the foundational era. We have to go back to the early 2000s. Neuroscience was in a very different place then.
Right.
We were obsessed with localization, finding the specific spot on the map that does the thing.
The X marks the spot era of brain science, phrenology, but with an fMRI machine.
Exactly. And the gold standard for proving that two mental processes are actually different things is something called the double dissociation.
Double dissociation.
Yeah.
That sounds like something from a spy thriller or a really bad breakup. What does that mean in neuroscience terms?
It's the ultimate proof, really. Basically, if I suspect that feeling and knowing are different systems, I need to find two specific types of patients. Patient A has lost the ability to feel but can still know.
Yeah.
And patient B has lost the ability to know but can still feel.
So if you can find those two opposite deficits, these two mirror images of each other, you've proven the systems are independent.
Correct. You've shown they aren't just two flavors of the same thing. And the paper that really truly nailed this down, this was the smoking gun, was published in the journal Brain back in 2009.
Okay.
It was by Simone Chimay-Suri and her colleagues. The title is a mouthful, but it tells you the whole story. Two systems for empathy. A double dissociation between emotional and cognitive empathy in inferior frontal gyrus versus ventromedial prefrontal lesions.
Okay, let's break down that mouthful because those are two very, very specific brain regions. Let's start with the first group of patients they looked at.
So group 1 had damaged lesions to the ventromedial prefrontal cortex. the VMPFC.
The VMPFC. Okay, let's place that for everyone listening. Where are we pointing if we're pointing at our own heads?
Okay, put your hand right on your forehead, sort of right between your eyes, and then go deep, straight back.
Yeah.
This is the front center of the brain. The VMPFC is evolutionarily newer. It is part of the executive suite, the CEO's office.
Okay, so these patients have damage right there in the CEO's office. What happens to them at a dinner party? What does this look like in real life?
It's fascinating. These patients had lost cognitive empathy. They really struggled with what we call theory of mind.
Theory of mind, the ability to know that other people have thoughts and feelings different from your own.
Exactly. So they couldn't understand what another person was thinking or believing. If you told them a sarcastic joke, they wouldn't get the intent. They'd take it literally. They just could not read the room intellectually.
They can't mentalize. They can't build a model of your mind in their mind.
Right. But, and here's the twist, the first part of the dissociation. If you show them a picture of someone crying or a video of someone in physical pain, they had a robust emotional reaction. They felt it.
Wait, so they're feeling this contagion of emotion. They're sad because you're sad, but they have no cognitive framework to understand why you are sad or what you're even thinking.
Exactly. The hot loop was firing perfectly. The cold loop was broken. Imagine feeling this intense, secondhand sadness, but having absolutely no logical way to process the context. It's just pure, confusing effect.
That sounds incredibly overwhelming. It's like catching a virus without knowing what a virus even is. You just feel the symptoms.
That's a great analogy. That's a perfect analogy. Now, contrast that with group 2.
Okay.
This is the other side of the dissociation. These patients had lesions in a totally different place. The inferior frontal gyrus, and specifically a region called Brodmann Area 44.
Brodmann Area 44. That sounds like a restricted military zone, like Area 51.
In the brain, it kind of is. This area is traditionally associated with speech production. It's part of Broca's area. But it's also a critical part of the mirror neuron system.
Mirror neurons, right. These are the neurons that fire both when I do something and when I see you do the same thing.
Yes. The ones that mirror action. And the IFG, the inferior frontal gyrus, is really the engine of that simulation. So what happened to these patients?
The opposite, I'm guessing.
The exact opposite problem of the first group. They lost affective empathy.
So the warm, fuzzy feeling is just gone.
Gone. They couldn't catch the emotion.
Oh.
If you showed them that same person with the smashed finger, they didn't wince. Their skin conductance didn't change. No sweaty palms. They didn't feel that phantom pain. But their cognitive empathy was perfectly intact.
So they could look at the situation
And logically deduce that person's in pain. They're likely angry at the car door. They probably need help. They could pass all the theory of mind tests with flying colors. They just didn't feel a thing.
That is so clinical. It sounds almost robotic. I compute that you are sad. Beep, boop.
It creates a very detached form of interaction, you're right. But this study was the breakthrough. It was the first time we had direct anatomical evidence that feeling and knowing reside in completely different zip codes of the brain. The inferior frontal gyrus is for simulation physically mirroring the other person.
A hot system.
And the VMPFC is for mentalizing, thinking about the other person.
The cold system.
A perfect double dissociation.
So we have these two headquarters, feeling in the IFG, knowing in the VMPFC. But I want to bring in another study from that same era because it highlights something we often ignore in neuroscience. We have this trope of left brain versus right brain.
Which is often exaggerated.
Right, it's often way overblown, but in this specific case, for empathy, it seems to lean really heavily to the right.
It absolutely does. You must be referring to the study by Catherine Rankin and her team, also published in Brain, but a little earlier, back in 2006.
That's the one. And this wasn't about sudden trauma or lesions. This was about slow degeneration.
Yes. They were studying a condition called frontotemporal lobar degeneration, or FTLD. This is a specific and really heartbreaking form of dementia. Unlike Alzheimer's, which tends to hit memory first, FTLD hits personality and social skills first.
I read about this. Families often say the person is still there intellectually. You know, they can do a crossword puzzle, they can drive a car, but their warmth, their personality, it just vanishes. They become like strangers.
Exactly. It's a loss of the social self. And Rankin's team used this disease as a kind of natural experiment to map empathy loss. They found that as empathy disappeared in these patients, it correlated with tissue loss in very specific areas, and they were predominantly on the right side of the brain.
So what are the coordinates? Where did the atrophy show up?
3 main spots kept popping up: the right temporal pole, the right fusiform gyrus, and the right caudate.
Okay, let's unpack those. The right temporal pole, that's near the ear, right? Kind of at the tip of the temporal lobe.
Roughly, yes. You can think of the right temporal pole as a library, but it doesn't store books. It stores social scripts.
Social scripts.
It holds the context of social situations. It's the part of you that knows what a birthday party feels like versus what a funeral feels like. It knows the unwritten rules of interaction.
So when that tissue withers away, you lose the instruction manual for how to be a human in a group.
You lose the semantic meaning of social cues, yes. Then you have the right fusiform gyrus. That's a famous one for face processing.
The face recognition area.
Right. And the right caudate, that's part of the basal ganglia,
Mhm.
involved in learning and reward. When this whole right-sided network collapses, the person doesn't just become mean, they become socially blind. They can't read faces, they don't understand context, they don't get the feedback.
So if the VMPFC and IFG from the Shumay-Sori study are the headquarters for knowing and feeling, these right hemisphere structures that Rankin found are like the data cables in the library that keep the whole operation supplied with information?
That is a perfect way to visualize it. And this early research, Shumay-Sori in 2009, Rankin in 2006, this really set the stage. By about 2010, we had the parts list. We knew for sure that hot and cold empathy were running on separate hardware.
But knowing the parts list isn't the same as knowing how the engine actually runs.
No, not at all. To really understand how we connect with people, how I actually catch your feeling from across the room, we need to zoom in on the hot loop. We need to really understand the mechanics of the simulation.
Let's go there then. Section 2, the hot loop, the nitty-gritty of feeling. You mentioned mirror neurons earlier, but I want to get more specific. How does my brain physically replicate your reality?
The core concept here, the fundamental idea, is shared representation. This is the idea that the brain doesn't just process other people. It, in a partial way, becomes them.
It runs a simulation of them.
A very, very visceral simulation. There's a seminal review paper by Christian Kiesers and Valeria Gazzola. It's called Neural Correlates of Empathy in Humans, published in 2018. They summarize years and years of fMRI data to show that when you feel an emotion and when you see someone else feel that same emotion, the brain activation overlaps to a significant degree.
Okay, give me a concrete example, something really primal.
Let's take disgust. It's a very powerful, very evolutionary emotion. Kiesers cites a classic study by a scientist named Wicker. They put people in an fMRI scanner and had them smell disgusting odors.
Fun day at the lab.
Science is glamorous. So they're smelling things like rotten eggs, spoiled milk. And when these people smelled the bad milk, a specific part of their brain lit up like a Christmas tree, the anterior insula.
The insula. We hear this name a lot in neuroscience. Where is it? Remind us.
It's deep in the fold of the cerebral cortex, kind of tucked away between the temporal and frontal lobes. The name insula actually means island. It's buried deep, and its main job is interoception.
Monitoring the inside of your body.
Yes, monitoring the internal state of your body. If your stomach churns, if your heart races, if you feel a blush coming on, the insula knows about it first.
So I smell the spoiled milk, my insula fires, I gag. Simple enough.
Right? But then, and this is the magic, this is the empathic leap, they showed these same participants a video of someone else smelling the spoiled milk and making a disgusted face.
But don't leave me hanging.
And the anterior insula lit up again.
Yeah.
In the exact same spot. The same voxels, which are like the 3D pixels in a brain scan, were active. Your brain was literally, physically recreating the sensation of disgust just by seeing it on my face.
That is wild. So the phrase, I feel your pain, isn't a metaphor at all.
Not neurally, no.
It's neural reality. My brain is hijacking its own hardware, its own disgust detecting hardware to simulate your experience.
Exactly. And it's the same for physical pain. Kiesers also discusses that famous study by Tanya Singer. When you receive a mild electric shock on your hand, your anterior insula and your rostral cingulate cortex fire up. When you just sit there and watch a loved one receive that same shock, those same areas fire up again. Not as strongly, maybe, but the location is identical. You are simulating their pain.
It really seems like the anterior insula is the absolute star of the show for this whole hot loop. What is it about this specific island of tissue that makes it so versatile? Why is it the hub?
The anterior insula is what we call a domain general region. And there's a paper by Isabella Muchler from 2013 in Frontiers in Human Neuroscience that really dives into this. It's called Structural Basis of Empathy and the Domain General Region in the Anterior Insular Cortex.
Domain general. Okay, so that implies it's a multitasker. It's not just for disgust or just for pain.
It sits the busiest intersection in the brain. It's like Grand Central Station. It integrates signals from the emotional centers, like the amygdala, the cognitive centers in the prefrontal cortex, and the sensorimotor body maps. the grand translator.
The translator, I like that.
It translates the visual input of seeing you cry into a somatic bodily feeling in my gut. It turns sight into feeling.
So people who say they're empaths, those people who seem to feel things really, really deeply, do they just have a better translator, a more efficient Grand Central Station?
Well, Muchler's team actually looked at that from a structural standpoint. She found that in healthy adults, the gray matter density, so literally how packed the neurons are, in the left dorsal anterior insular cortex correlated with their self-reported empathy scores.
So wait, if I'm a naturally empathetic person, I might physically have a denser, more packed insula. I literally have more hardware in the hub.
That appears to be the case, yes.
Yeah.
You have a higher fidelity simulation engine, so to speak. Your brain is better at recreating the feelings of others.
And here's where I want to push back a little bit. Is feeling the pain enough? Because if I just feel your pain, if my high fidelity insula simulates your trauma perfectly, I might just get overwhelmed.
Right.
I might panic. I might just run away to protect myself from this horrible feeling. That's not really helpful empathy, is it? It's just distress.
You have hit on the crucial distinction, and this is really where the research shifted in a big way around 2018. We had to separate emotional empathy, which is just the infection of feeling, the contagion from empathic concern, which is the motivation to actually do something to help.
So the difference between I hurt because you hurt and I care that you hurt and I want to fix it.
Exactly. Abigail Marsh wrote a fantastic review in Current Opinion in Behavioral Sciences in 2018 called The Neuroscience of Empathy. And she highlights that these two things are structurally distinct in the brain. Empathic concern, that drive to help, is linked to the ventral striatum and the subgenual anterior cingulate cortex.
The ventral striatum. Hang on, isn't that the reward system? Dopamine, pleasure.
It is, which suggests that true compassion, the act of helping, has a rewarding quality to it. It actually feels good to help someone. But pure emotional empathy, driven just by the insula, can be purely stressful. If you have too much insula activation and not enough of that ventral striatum reward system activation, you get burnout.
That explains so much about caregiver fatigue. It's an overdose of the insula without the protective, rewarding effect of the ventral striatum. It's all cost and no benefit.
Exactly. And there's a more recent paper from 2023 that really drives home the insula's specific role in the intensity of the feeling. This is by Holtman and his colleagues, published in Cerebral Cortex. The title is Effects of Emotional Valence and Intensity on Cognitive and Affective Empathy After Insular Cortex Lesions.
So what did they find about its causal role?
Holtman's team confirmed that the insula is causal. It's not just correlated. Patients with lesions there specifically lost the ability to share the intensity of another person's emotion.
The intense?
They could still identify the emotion. They knew the person was sad or happy, but the volume knob was turned all the way down. They felt a whisper instead of a scream.
The volume knob. That is a great image. So the insula provides the volume, the intensity, the hotness of the shared feeling. But without the other systems chiming in, it's just noise. It's not necessarily helpful.
Correct. And to make sense of that noise, to give it meaning and context, we need the cold loop. We need the system that provides the understanding.
Okay, let's move there. Section 3, the cold loop, cognitive empathy. This is the mentalizing network we touched on earlier with the VMPFC, the CEO's office.
This is where we act as detectives. We're not feeling, we're inferring. We use context, memory, and logic to figure out what someone is feeling. And a key paper here is from 2011 by Knut Schnell and colleagues in the journal Neuroimage. It's titled Functional Relations of Empathy and Mentalizing, an fMRI study on the neural basis of cognitive empathy.
I remember looking at this one in the notes. They used a really clever experimental design with cartoons, right?
Yes, it's very elegant. They showed participants these simple cartoons of a character, but the character had no face, no eyes, no mouth, no expression at all.
So you couldn't use the mirror neuron system. You couldn't mimic the smile or the frown because there wasn't one. The insula had nothing to grab onto, no emotion to mirror.
Exactly. You were forced to look at the situation. Maybe the character is tripping over a rock or receiving a gift, and you had to infer their internal state based on the context alone.
Purely cognitive work. And what parts of the brain lit up for this faceless empathy?
The mentalizing network, loud and clear, the dorsomedial prefrontal cortex, DMPFC, the superior temporal sulcus, STS, and the temporal poles. This is classic top-down processing. But here is the aha moment that Schnell's team found.
Okay.
Cognitive empathy also recruited the left amygdala and the hippocampus.
The hippocampus, the memory center. Why would cold logic need the memory center to figure out a cartoon?
This was a huge insight. It's just that even when we are doing cold intellectual empathy, we are referencing our own emotional memories. We're searching our internal database. I remember a time when I tripped over a rock. It was embarrassing, but also a little funny. We use that autobiographical memory to inform our cognitive understanding of the character.
So it's not purely cold after all. It's cold logic accessing hot data from your own past. It's like a librarian looking up an old emotional diary entry.
That's a beautiful way to put it, yes.
Yeah.
And structurally, this system looks very different from the affective system. In 2019, a researcher named Uribe and his colleagues published a study in Frontiers in Behavioral Neuroscience. The title was Neuroanatomical and Functional Correlates of Cognitive and Affective Empathy in Young Healthy Adults.
This is the study comparing brain volume versus thickness, right?
Yes, and the distinction really matters. They found that high scores in perspective taking, which is the core of cognitive empathy, were associated with greater cortical thickness in the neocortex.
So a thicker outer layer of the
A
brain.
thicker cortex, yes.
Yeah.
Specifically in the left orbitofrontal cortex, OFC, the ventrolateral prefrontal cortex, VLPSC, and the anterior cingulate.
And the neocortex is the evolutionarily newer part of the brain, the executive suite we talked about.
Exactly. So while affective empathy, the HOT system, often relies on the volume of deep, ancient structures like the thalamus and amygdala, cognitive empathy relies on the thickness of the neocortex. It's a higher order, more evolutionarily recent, and frankly, more metabolically expensive computation.
So if I can try to summarize this, we have a hot loop running on the volume of deep ancient structures and the insula. Then we have the cold loop running on the thickness of the outer layer of the prefrontal cortex. But the real magic, and this seems to be the focus of the last few years of research, is what happens when they talk to each other.
That brings us perfectly to Section 4, Network Dynamics and Connectivity. This is the major shift that happens around 2018. We move from what some neuroscientists jokingly call blobology.
Blobology?
Just seeing what areas, what blobs light up on a scan to connectivity. How are these different parts wired together? What are the highways between them?
So we're looking at the wiring diagram now, not just the individual components.
Yes, and to understand this, we have to go back to a foundational paper from 2012 by Cox and his team in Social Cognitive and Affective Neuroscience. It sort of set the baseline for this kind of thinking. The title is The Balance Between Feeling and Knowing. Affective and cognitive empathy are reflected in the brain's intrinsic functional dynamics.
Okay, and they looked at resting state connectivity. This is what the brain is doing when it's supposedly doing nothing, right? Just idling.
Yes, just idling in the scanner. And it turns out your brain's idle mode tells us a lot about your default empathy style. Cox's group found that people who lean toward affective empathy, the natural feelers, have stronger resting connectivity, stronger communication between the ventral anterior insula, the orbitofrontal cortex, and the amygdala.
So the hot loop is always humming in the background for them. The engine is just idling higher. The phone lines are always open.
Exactly. The lines of communication are wide open and well maintained. But people who lean toward cognitive empathy, the thinkers, they show stronger connectivity between the superior temporal sulcus, STS, which tracks biological motion and infers intent, and the ventral anterior insula.
So their idle state is wired more to analyze intent and action, not just to generate raw feeling.
Precisely. Their default is to figure out why someone is doing something. But the most surprising, and I think most interesting, finding on connectivity comes from that Uribe 2019 paper we mentioned a minute ago. They looked at the brains of people with low affective empathy scores.
Okay, so the people who don't naturally catch the feelings, the people we might unfairly label as cold or detached.
Right. Now, what would you expect to see in their brain wiring?
I'd assume. Just less connection, weaker signals, broken wires maybe. That would be the logical assumption.
That's what everyone thought. But Uribe's team found the exact opposite in one specific circuit. Individuals with low affective empathy showed increased connectivity between the orbitofrontal cortex and the anterior cingulate.
Wait, increased connectivity. Why on earth would a low empathy brain have stronger wiring? That seems completely counterintuitive.
The interpretation is fascinating. It's thought to be a compensatory mechanism
Compensatory?
because they don't get that automatic bottom-up intuitive emotional hit from the insula. They have to over-engage their cognitive executive pathways to consciously figure out what's going on.
That is incredible. So it's like they're running an emulator. I don't feel it automatically, so I have to compute it manually. And that manual computation requires a stronger connection, more bandwidth.
Exactly. and that takes more cognitive effort.
Mm.
It suggests that what we might perceive as low empathy from the outside might actually be high-effort cognitive processing on the inside, trying to fill the gap. They aren't indifferent. They're just processing the social data through a logic gate instead of a feeling gate.
That fundamentally changes how I view people who seem detached or clinical. They might be working harder than anyone else in the room just to understand what's happening on a social level.
They might be. And this leads us to the modern integration model. We have a 2024 review by Almeida and others in Brain Sciences. It's called Neuronal Correlates of Empathy, a systematic review, and also a really important 2021 paper by Stevens and Tabor in Neuropsychology.
Okay, so what is the synthesis here? How do they propose this whole pipeline works in a perfect empathic scenario?
Stevens and Tabor propose a clear hierarchical flow, a three-step pipeline for a complete empathic experience.
Okay, walk me through it. Step 1.
Step 1, the spark. This is affective empathy. The insula and the amygdala fire. You catch the feeling, there's a sudden signal. Something is happening here. Pay attention.
Okay. The hot system fires first. That's step 2.
Step 2, the regulator. Cognitive empathy kicks in. The medial prefrontal cortex and the temporoparietal junction, the mentalizing network, they jump online to analyze the signal. They give it meaning. He's crying because he just won, or he's crying because he's hurt. Crucially, they regulate the distress so you don't just drown in it.
So the cold system comes in to manage the hot system's alarm. And step 3.
Step 3, the action. This is compassion or empathic concern. The ventral striatum and the subgenual ACC activate, and they drive you to do something helpful, to offer a hand, to say a kind word.
Spark, regulator, action. It's so clean.
But here is the critical part, and Stevens and Tabor point this out very clearly, the failure point. If step 2 fails, if the cognitive system fails to regulate that effective spark,
The regulator breaks down.
yes, you don't get compassion, you get personal distress.
You just get overwhelmed. You drown in the other person's feeling, and you have to withdraw to protect yourself.
Exactly. If the prefrontal cortex doesn't successfully dampen the amygdala's alarm bells, the empathy turns toxic for the observer. You aren't helping anymore, you're just panicking. And this confirms that being good at empathy isn't about feeling more, it is about effectively regulating what you feel.
That is a massive takeaway, a huge one. We often think the most empathetic people are the ones who cry the hardest at the sad movie. But actually, the most effective empaths are the ones whose prefrontal cortex can hold that feeling, analyze it, and then channel it into helpful action.
Precisely. It is about the structural integrity and connectivity of the executive brain, not just the volume or reactivity of the emotional brain.
Now, this whole pipeline, this beautiful spark regulator action model, it doesn't happen in a vacuum. It gets modulated by other things.
It does.
And we have to talk about Section 5, modulation and context. We have to talk about the things that turn the volume up or down on this whole system. And one of them, unfortunately, is bias.
This is a tough reality of our neural architecture.
Yeah.
In 2018, Xi Han published a really important review in Trends in Cognitive Sciences titled Neurocognitive Basis of Racial In-Group Bias in Empathy.
Okay, what did the data show?
It showed quite clearly across multiple studies that the automatic affective empathy response, that firing of the anterior cingulate and the anterior insula when we see someone else in pain, is significantly weaker when we're viewing an outgroup member compared to an in-group member.
An outgroup in these studies was defined by race.
In these specific studies, yes. But other research suggests it extends to all sorts of other tribal boundaries, political affiliation, which sports team you root for, you name it. The mechanism suggests that this automatic system isn't actually fully automatic.
It's gated.
It is gated by top-down cognitive attitudes.
So before the insula even gets the green light to simulate the pain, the prefrontal cortex has already made a quick subconscious us versus them calculation and either opened the gate or closed it.
It appears so. Our cognitive attitude, our bias, acts as a filter on the affective input. We literally, neurally feel less for those we categorize as other.
That is deeply sobering. But I suppose knowing it is the first step to overriding it, right? If it's a top-down gate, then we can consciously change the top-down attitude that's controlling the gate.
Absolutely. That is the hope of cognitive control. If we can consciously expand our definition of in-group to include more people, we can theoretically open that empathic gate for the insula.
And speaking of cognitive control, that brings us to aging. Because the empathy brain doesn't stay the same as we get older, does it?
No, it adapts. It has to. This brings us to the Moore et al. Study from 2016 in psychiatry research, Neural Imaging. The title was distinct neural correlates of emotional and cognitive empathy in older adults.
So what did they find about what successful empathy looks like in an aging brain?
It's another counterintuitive finding. They found that in older adults, high affective empathy was linked to the ability to deactivate the amygdala and insula during cognitive tasks.
Deactivate. So the secret to being more empathetic when you're older is turning off your empathy centers.
Turning them down. It's about neural efficiency. As we age, the brain just gets a bit noisier. There's more background static. To focus on the difficult cognitive task of understanding someone's complex situation, you need to be able to turn down the emotional noise from your own brain.
So the older adults who were best at empathy were the ones who could effectively hush the hot loop when they needed to really think.
That's right. It goes back to that regulation point we made earlier. It's not about maximum power. It's about efficient control and resource management.
It's not about having the loudest alarm. It's about knowing when to turn it on and when to turn it off.
Exactly. It suggests that wisdom, neurally speaking, is the ability to manage your own internal interference.
So let's bring this all together. We have come a very, very long way from empathy is just a warm, fuzzy feeling.
We certainly have. We started with those foundational legion studies from the 2000s, Schmidt, Suri, and Rankin, which proved structurally that feeling in the IFG and knowing in the VMPSC are separate things.
Then we zoomed in. We looked at the hot loop, the anterior insula acting as the simulation engine, giving us the volume and intensity of the experience, and then the cold loop, the thick prefrontal cortex, using memory to contextualize that experience.
And finally, we got to the modern connectivity view from the work of Urey, Stevens, and Almeida. The idea that it's all about the dynamic flow between these systems. The spark from the insula needing the regulation for the prefrontal cortex to lead to the action of compassion.
It really changes how I look at people. When someone seems cold, maybe their brain isn't broken, maybe they're just running that compensatory wiring we talked about. They're processing deeply, just differently.
And that raises a really provocative final thought for me, based on that Uribe 2019 study. If low empathy brains are wired with these over-connected cognitive loops, that stronger highway from the orbitofrontal cortex to the anterior cingulate, are they really low empathy? Or are they just processing social data through a different, purely logical algorithm?
And if that's the case, the big question is, can we train it? If cognitive empathy relies on cortical thickness in the orbitofrontal cortex, can we exercise that part of the brain? Can we literally thicken that cortex through specific training and turn that cold understanding into warm compassion?
That is the frontier of this research. Everything we know about neuroplasticity suggests the answer might be yes.
Yeah.
We might be able to train the brain to build better, stronger bridges between the hot and the cold systems.
A hopeful note to end on. Empathy isn't just a trait you're born with. It's a neural system you can understand, you can navigate, and maybe, just maybe, you can even upgrade. Thank you for this incredible deep dive.
My pleasure. Fascinating.
And thank you for listening. Keep those synapses firing. We'll see you in the next deep dive.